Hi, today we will be looking at a common physics problem that involves the applications of Newton's second law, in this case where the net force is equal to 0. Here's the problem. We are considering a rock climber of mass of 50 kilograms who is ascending a vertical wall and stops for a rest by leaning back on the rope as seen in the diagram. The rope has an unknown tension and makes the angle of 31 degrees with the vertical. As the climber rests, the wall exerts a force of unknown magnitude, and this force points at an angle of 15 degrees above the horizontal. First, we want to start with what we know from the problem. We know that the climber has a mass of 60 kilograms. The rope has an unknown tension, which makes a 31-degree angle with the vertical. The wall exerts an unknown force 15 degrees from the horizontal, and the climber is not moving. Therefore, Fnet in the x and y directions are 0. It's a pretty safe bet that in this case we'll be solving for both the unknown tension forces. And here, sure enough, the first question asks us to determine the magnitude of the tension in the rope to remain stationary. And it wants us to start from a fundamental principle, so we will do that. The fundamental principle here is dp dt equals 0, same as Fnet is equal to 0. So first step, we're going to break Fnet into the x and y components. Here I have determined that to the right is positive and to the left of the climber is negative. So therefore, the force of the wall times cosine 15 is going to give us that horizontal angle to the horizontal force to the right, minus the tension force times sine of 31 is going to give us that horizontal component to the left, and that's going to be equal to 0. We have Fnet in the y, and here again I have designated above the climber to be positive and forces pointing down to be negative. So we have the force of tension times cosine 31 is going to give us that vertical tension force plus the force of the wall times sine 15, which is also going to give us vertical up force, and then minus the weight force, or mg, which is always pointing straight down. And a note here is that these forces are magnitudes. They're not vectors. So we have two variables and two unknowns. So we're going to solve for one of the variables and then plug it into the other equation. The first variable we're going to solve for is the force of the wall. So using some algebra, we change force of the wall is equal to force of tension times sine 30 divided by cosine 15. And that is just gotten from this first equation, Fnet in the x. Then we plug F-wall into the equation for Fnet in the y, and we get this one right here, Ft cosine theta plus Ft sine theta sine 31 divided by cosine 15, all times sine 15 minus mg equals 0. See, and we bring the tension force out to the left because that is what we're solving for, and in doing that we get mg divided by cosine 31 plus sine 31 plus tan 15. Plugging in the variables that we already know, they're given in this problem, we have a force of tension of 591 newtons. Alright, the next question it asks is to determine the magnitude of the wall force to remain stationary. And we're also starting from a fundamental principle again. So we have Fnet is equal to Fnet in the x direction plus Fnet in the y direction, all equal to 0. Once again, we're going to use these force components to solve the problem. So in this case, we only need Fnet in the x because we are only solving for the force of the wall, and we already know force of tension, so there's no need to use both formulas in the x and y directions. So we have the magnitude of the wall force times cosine 15 minus the magnitude of the tension force times sine 31 is equal to 0. A little simple algebra will get us that the magnitude of the wall force is equal to the net force times sine theta, the magnitude of the net force times sine theta divided by cosine 15, or sine 31 divided by cosine 15, and we have the magnitude of the force the wall force is equal to 315 newtons when we plug in the data given from the problem. And the last question asks us to calculate the minimum static coefficient of friction between the climber's shoes and the cliff required to remain motionless in the position. So there are a couple of concepts. We need to realize that we're talking about static friction, since we want to know when the climber is not moving. And this friction will be at a maximum right before the shoe slips. And this is what we are looking for. So we have a couple definitions for the force of friction. We know that the force of friction is equal to mu Fn, in this case mu of static friction. And Fn in this case, which always points perpendicular to the surface, is the magnitude of the wall force times cosine 15, which will give us this perpendicular force right here. And then and the force of friction is also equal to magnitude of the wall force times sine 15. So in order to solve for mu of the static friction, we set these last two formulas equal to each other. We have mu of static friction times magnitude of the wall force times cosine 15 is equal to the magnitude of the wall force times sine 15. And then we solve for mu s, which is equal to the force of the wall magnitude times sine 15 divided by the magnitude of the wall force times cosine 15. These wall forces will cancel. Sine 15 over cosine 15 is equal to tan 15. Plug that into the calculator and we get 0.268. And remember, this value is unitless. Thank you.